Uh, our next speaker is Liheng Zheng, who will tell us about a universal advection-diffusion equation solver based on stochastic differential equations method. And if you want to go ahead and share your slides.
Okay, can you hear me loud and see my slides?
Yes.
Okay. Okay, I will.
You may want to use the swap display button at the very top because we're seeing the presenter view on these slides. If you look at the top
Sorry.
left, there's a swap displays. There we go.
Okay. I would use laser pointer. Okay. So I will talk about a universal advection-diffusion equation solver, which is a Fortran library mainly written using Fortran 2008, which is an objective Fortran. And the name of the library is acronymed UBA for Universal Boltzmann Equation Solver. It is publicly available from GitHub, and it is also listed at EMAC. A paper describing the library is published in Geoscientific Model Development. The library was originally developed as a kinetic equation solver for particle distribution functions in the terrestrial magnetosphere. However, the library is very powerful. It's very versatile and flexible, so it makes it potentially useful in many other scenarios out of the Earth. UBA solves a general form advection-diffusion equation given here in the user-specified curvilinear coordinates and user-specified boundary conditions up to 3 dimensions. So to the left of the equation, it is a convective derivative of the distribution function, and to the right are the terms describing diffusion process, advection process, and source and loss. Note that the source and loss can be both dependent on the unknown function and independent of the unknown function. UBA is particularly advantageous in dealing with cross diffusions, which means this diffusion coefficient tensor have off-diagonal components in multiple dimensions, which is notoriously difficult for finite difference methods. The theory behind the UBA library is the stochastic differential equation theory. In this theory, a solution of the advection-diffusion equation at t0 and x0, x is a spatial coordinate, t is time, is given by the Feynman-Katz formula written here. From right to left, the capital X stands for stochastic path started at t0 and x0. Let's look at a 1D illustration here. So if we want a solution at t0 and x0 in the domain, the solution is obtained by launching a huge number of stochastic paths. The stochastic motion is described by the advection-diffusion equation. It's the underlying stochastic motion described by the equation. So this capital X stands for a path. The path can either the stochastic motion travels backward in time. It can either stops at the initial condition or stops at a boundary condition of the first kind at a boundary of the first kind boundary condition. Note that the shape of the first kind boundary can be time dependent. To the left, the boundary is of a Neumann type boundary condition, so the stochastic process is reflected on that boundary. Capital F is a functional of the stochastic path. So given it a specific stochastic path, this functional returns you a value. And the Feynman-Katz formula says that the solution at this t0 and x0 is equal to the expectation value of the functionals of many stochastic paths. So in practice, we need to launch from thousands to tens of millions stochastic paths to calculate this expectation. It's basically calculating the arithmetic mean of these functional values. Uber uses sophisticatedly designed schemes to enhance its computational efficiency by 1 order of magnitude over straightforward Monte Carlo methods. If you straightforwardly implement the Monte Carlo methods, like I discussed here, it will be very slow. And Uber is also highly parallelized. In the test, Uber was sped up by 6.7 times over its serial execution using 86 CPUs. In this test, this is a numerical experiment that we did. The x-axis is the number of CPUs we use. The y-axis is the speed up. The speed up, for example, a speed up of 2 means that the code runs at a speed twice as fast as its serial execution. So the dashed line here is the theoretical prediction, and the blue crosses are numerical experiments using Uber. So we can see that the last data point is the point using 86 CPUs. We can see that at using 86 CPUs, the speed up is already approaching its theoretical minimum of the speed up using parallel computations. The trade-off for Uber's great ability and flexibility is that it is generally slower than finite difference solvers. In our test for 1D problems, the fully parallelized Uber is still about 1 order of magnitude slower than a serial finite difference solver. However, Uber was not designed to be used on 1D problems. For multidimensional problems, the speed comparison would improve in Uber's favor because its computational complexity doesn't change with dimension. But for finite difference methods with higher dimension, the computational complexity would greatly increase. The library is used as this. The user specifies his or her mathematical problem by inputting the listed input data and the functions here to the library following a well-commented template. In this list, the first one is the gradient of the logarithm of the Jacobian determinant of your coordinates, of your curvilinear coordinates. So this field tells the library the geometry of your curvilinear coordinates. The second lines are the coefficients of the equations, which can be 0 if there's no such term. The following are the initial conditions, the equations to describe the boundary geometry, and for each piece of boundary, the boundary conditions. And after you have done this, implementing the equation solver is as easy as in 3 lines. You initialize Uber. You have an input file that stores your the locations and the times that you want the solutions, and the output file that stores the output solutions from Uber. And then you call the solver. And after solving the equation, you call finalizer to release the memories claimed by the solver. And MATLAB scripts to generate and process these data files are also provided along with the library. We look at an example application of the library. We used Uber to simulate a relativistic electron flux generated by cosmic ray albedo neutron decay in Earth's radiation belt. Cosmic rays generate relativistic electrons in the upper atmosphere due to neutron beta decay. This process is called the cosmic ray albedo neutron decay. The generated electrons are then trapped by the planetary magnetic field to form a radiation belt. So in this process, there are several physical processes taking action. The electrons are drift around the Earth. There are Coulomb scattering of the electrons. The electrons will precipitate into the atmosphere to be lost. And there are this cosmic ray albedo neutron decay source. So in these plots, the x-axis is a geomagnetic longitude. So the electrons, as they drift from west to east around the Earth, their geomagnetic longitude will increase along this axis and then turn around. The y-axis is the electron pitch angle in the magnetic field. The black region here, electrons in the blank region here are lost into the atmosphere, so there's no electrons in the blank region, and the edge of the blank region is is a boundary of the problem. This panel shows you the intensity of the Coulomb scattering. This panel shows you the intensity of the current source to generate the electrons. And the bottom rows shows you the simulated electron flux from a blank radiation belt after 2 hours and after 10 hours. There are two electron populations. One population is above 60 degrees of pitch angle. These electrons could be stably trapped by the magnetic field. And you can see that their intensity steadily increase. It is increased by roughly 1 order of magnitude over 8 hours. Another population below 60 degree pitch angle, the electrons are not stably trapped. They are wiped out by South Atlantic anomaly of the Earth's geomagnetic field. So that after each drift period, the electrons will be wiped out by this South Atlantic anomaly. So you can see that the electron distribution function in this region do not change over time because they are wiped out after every drift period. And you can see that immediately after this South Atlantic anomaly, the regions are basically empty of electrons. And as they drift toward the east, more electrons are generated by the current source, and you can see an increasing in the flux distribution. More examples of the UBAC applications are provided in the GMB paper as well as on UBA's GitHub page. And lastly, I would like to thank you all for listening to my presentation and thank NASA for funding our research. That's it. Thank you.
Thank you very much. So is this, it sounds like this application is coming more from the earth science community rather than the astronomical community, even though of course there's a big overlap when you're talking about
Yes.
interplanetary magnetic fields and things like that.
Yes.
And I was just curious because just some of the other earth scientists I've talked to have told me that MATLAB is the language of choice, the high level language in the earth science community. So is that what you find as well?
You mean the language of the code?
Well, for the visualization, for the scripts.
Oh, I think there are two major choices. One is Python and one is MATLAB. I happen to use MATLAB.
Oh, okay. So we have a couple minutes before the next talk if anybody would like to ask questions. One thing that occurred to me is, so I've never tried to handle a system in which the diffusion coefficient depends on the direction, but I was wondering if operator splitting works in that situation.
Yes. Generally for 2D or 3D diffusion problems, including the cross diffusion term, for finite difference methods, they use the operator splitting method, and that could be very computationally expensive.
Okay.
Yes.
Okay. Well, if there are no more questions, then let's go ahead and thank Liheng again for that talk.